12 I pulled, and you won't see it on yours. So this will be your 12. The number of employees who work nights and weekends at a department store is summarized in the table below. Let N represent the event works nights and W represent the event works weekends. Based on the table, are N and W independent events? I would say probably not, just if I used common sense, but let's check the math here. The big question is do we have overlap? That's the big thing. Do we have overlap? Are they truly disjoint? But anyways, let's just go through and check some stuff. It says yes because the P of N times P of W is equal to the P of N times W. All right. So that's an and statement. The probability of working nights and weekends. Remember, that means and. Probability of working nights and weekends. So that's right there is the working nights and weekends. And by the way, you need a running total here. You've got 48, 72, 120. So the probability of nights and weekends is going to be 8 in 120, which reduces down to what? 4 in 30, 2 in 15. All right, so this right here is an independent formula, okay? So the probability of nights is going to be 20 in 120, and the probability of working on the weekend is going to be 48 in 120. Anyways, what's that reduced to here? We got 10 over 12, 5 over 6, 24 over 30, 12 over 15. Boy, I lost my place here. Those are both divisible by what? 4 would be 12 over 30. That's divisible by 3, 6 actually, 2 over 5. I don't know what that says. 20 over 120 is 1 over 6. All right, so let's see if this is true or not. We take a sixth, we multiply it by 2/5, and we get 2/30, we get 1/15. No. So this is a maybe, right? It looks like they are not independent. And this is the one. Yes, because the probability of nights times the probability of weekends is not equal to the probability of nights times weekends. So we did a test for independence, and I know that bothers some kids, but if independent, the probability of event A times the probability of event B must equal the probability of A and B, all right? Or the probability of event A plus the probability of event B must equal the probability of A plus the probability of B. Those are your two checks for independence or not. All right, 14 or 13, whatever it is on yours. The results of a survey of the student body at Central High School about television viewing preferences are shown below. Are the events student is male and student prefers a reality series independent of each other? Justify your answer. So student is male and a student prefers reality series. Are they independent? Probably not, because there's overlap. Like, that's the big thing. But anyways, we're gonna do the check. So we're gonna see this is the probability of being a male times the probability of enjoying reality series equal to the probability of being male and reality. That's the question. So the probability of being a male is 230 and 490, or 23/49. The probability of enjoying a reality series is 180 and 49, or 18 in 49. The probability of being both is 70 in 490, or 1 in 7. So are these the same? Probably not. I got a 414 up top. Bottom's 49 times 49, 24/1. Nope. So not independent. Because these two didn't match. All right, moving forward. And I know those are going to be rough on kids. It's, not just knowing a formula, understanding what the formula is useful for. All right, 15 is find 10C4 by hand. So the NCR formula is n factorial over r factorial n minus r factorial. So this is n, this is r. 10 choose 4. So we're going to have 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Notice it says by hand, so I'm expecting to see this stuff written out. Over r factorial, which is 4 times 3 times 2 times 1. Next to n minus r, which is going to be 6. 6 times 5 times 4 times 3 times 2 times 1. And what will have happen here is those guys will disappear and those guys will disappear. Because they're common factors of numerator and denominator. What are we left here with? We're left with 10 times 9, which is 90, times 8, which is 720, times 7, which is going to be 5,040. And we will check ourselves here, okay? The bottom's 4 times 3 times 2 times 1. And there's some other stuff I could have done here. Like, you guys may not be familiar with stuff like this, but you can do this. Make that a 2. Then you can throw away that 2, okay? And I'll double check it that way. So 5,040 over 12, 24. Both even. 2520 over 12, both even. 1,260 over 6, still even. 630 over 3, and 630 is divisible by 3. It really is. What would that be? 210? So anyways, I was doing some simplification up here. 10 times 9 is 90, times 7 is 630 over that 3. Same thing right there. And that's what I get by hand. Now, I realize you're going to use a calculator to figure out what 10 times 9 is. Like, I get it. But anyways, show the steps, show the process, okay? All right, find 12P3 by hand. 12P3 is pretty ambitious for by hand. I don't even know if I want to do it by hand, but I can write it out, okay? The NPR formula is n factorial over n minus r factorial. So this thing's going to be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And down here we would have 12 minus 3, right? N R, 12 minus 3 is 9. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And just asking kids to write all that out is like pulling teeth. You don't want to do it. Anyways, common factors cancel. And we're doing 12 times 10, which is 120, times 11, which is 1,320. That seems right. 1,320. I'm going with it. All right, so now next to a nice easy one. I realize that was so much for some of y'all. Carlos owns 3 pairs of shoes, 2 pairs of pants, 5 shirts, and 12 hats. How many possible outfits can Carlos wear? This is the fundamental counting principle. All you gotta do is multiply all the numbers together. It's 3 times 2 times 5 times 12. So what do we have here? We have 3 times 2, which is 6, times 5, which is 30, times 12, which is 360. Because Carlos has a lot of hats. 12 hats. Kind of weird, huh? Anyways, that's how you do the fundamental counting principle. All right. Class officers are to be picked from a pool of 20 students. The officers are president, vice president, secretary, and treasurer, and those are ranked positions, so order matters, which means I get to use a permutation. How many possible groups of 4 can be created from a pool of 20? It's a permutation. We're doing NPR, okay? 1, 2, 3, 4, 20. It's 20, pick 4. That's all it is. 20, pick 4. And I'm not gonna do this by hand. You don't have to on this one. Unless I say I want it done by hand, you don't have to do it by hand. You're gonna hit math, probability, NPR. It's 20, pick 4. A whole lot of combinations, 116,280. All right, find the complement of the following events. So, the complement is merely the probability of the event not happening. Okay? And, you know, it's not obvious to kids sometimes, but all you do to find a complement, you take the probability of the event away from 1 or 100%. Remember, 1 is 100%. I hope you do. You should. So we're just going to take these things away from 1. That's all we're going to do. And we're going to use some correct notation here. That's one of the ways I can put very good distractors on a test, okay? I can do things like that. Now, the complement of an event would simply have a bar sign over it. So, the complement of the probability of A or B would be called the probability of A or B bar over it. And it's 1 minus 3/5. And God bless you if you're using a calculator. Like, 1 is 5/5, you're taking away 3/5, you're gonna get 2/5. Just, you know, don't breed, kids. It's not that hard. I don't know what you've been doing in school, but evidently in school. This one would be kind of hard, funny to write. The complement of A given B bar. It's gonna be 1 minus 0.99. And I'm sure you're gonna go push buttons in a calculator, but it's gonna be 0.01. This one would be the probability of not A. And it would be 1 minus 3/4, which, you know, if you can't think about dollars and quarters, I don't know. 1/4. That ought to be an easy problem. Will kids miss it? Oh yeah. Oh yeah. 21, how many different arrangements are there for the word Tennessee? So the idea here was is we do n factorial over n1 factorial, n2 factorial, n3 factorial, dot, dot, dot. So we're just gonna count letters here. There is 1 T, there's 1, 2, 3, 4 E's, 1, 2 N's, 1, 2 S's. Okay, that's the things I have to do. And Tennessee itself has 4, 6, 9 letters. So this thing's gonna end up being 9 factorial over, we don't have to talk about 1 factorial, because remember 1 factorial is 0. It's defined to be that way. But, you know, you can write it in if you want to. Over 4 factorial, 2 factorial, 2 factorial. That's how you figure it out. I'm not going to write that out. Anyways, let's just do it this way. Math num n over d. We have 9 math probabilities where you'll find the factorial, choice 4. That is over 4 factorial. Two factorial. And another 2 factorial. $3,780. 3,780 gibberish words can be made from the word Tennessee. And I believe this is the last one, which makes me happy because I won't eat my breakfast. 3 marbles are to be drawn at random without replacement from a bag containing 15 red marbles, 10 blue, and 5 white marbles. What is the probability of drawing 2 red marbles and 1 white marble from the bag? So I think I put this one in here so that I could show you how to do this with combinations, permutations, but you don't have to. Now, you do need to realize this. There's a lot of, it does not specify order. Okay, there is no order specified. But you have to think about the scenarios here. And this is what makes this one horrible. You could be red, red, white. You could be red, white, red. You could be white, red, red. There's 3 scenarios that you have to run through because that's how many ways you can arrange 3 different things. Or sorry, that doesn't seem right. Am I missing something? I guess since they're red, it doesn't make a difference. But you could be red, red, white, red, white, red, white, red, red. I don't think I'm missing anything. So these are your 3 scenarios. So we're doing this without replacement. They're all going to have the same probability. So the probability of getting a red marble, let's see, we got 15, 25, 30. There's 30 marbles. That should probably be mentioned. Probability of drawing a red is going to be 15 and 30 initially. And then we draw another red, it's going to become 14 and 29. And then we draw a white, there's now 28 marbles in there. But I haven't pulled a white yet, so there's going to be 1 white. By the way, it was this or that or that. So that's important too, because we know that the word or means add. And this is red and white, and means multiply. So we go through this process again. This is 15 over 30. Here we've got, I don't know why I chose 1. There's 5 white marbles. Now we've got to white, it's going to be 5 over 29. And now we're back to red, which is now 14 and 28. Now notice that the numerators are all the same, and even though things are out of order, the denominators are all the same. These are all the same number. They all have the same likelihood of happening. All right, this is white, red, white. There are 5 of 30 at this point in time. Now there's 29. Then there's going to be 28. Now we're at red, 15 and 29. Pull another red, 14 and 28. So again, all 3 of these are the same exact number. So I'm just going to do it once. What do we got here? We got a 15 over 30 times a 14 over 29 times a 5 over a 28. Now we'll convert to a fraction, will it? It does. 505 and 1/16. And they're all going to be the same thing. So 5 plus 5 plus 5 is 15 in 116. That's the probability of doing that. And there is a way to do that with permutations. I just don't care to show it because it's too early in the morning for me to be thinking about permutations right now. So there's your twin. I hope the test goes well for you. I'll be honest, I don't have high expectations on this one. But surprise me. Prove me wrong. I would love to be proven wrong. So prove Milbrath wrong.